Look down at a modern heap leaching pad, and the scale is staggering. These are mountains of crushed rock, terraced and engineered to extract trace amounts of gold spread across millions of tons of material. The entire operation exists to achieve one specific reaction: maximizing the physical contact between the gold ore particles and a leaching reagent, like sodium cyanide or a modern eco-friendly alternative. But despite the macro-scale infrastructure, the yield of this massive pad is dictated entirely by what happens at the microscopic level, deep inside the void spaces of the heap. Getting that reagent down into those microscopic voids reveals a major operational bottleneck. It comes down to how the chemical is actually delivered through the pipeline to the surface of the ore pile. The industry relies on two primary delivery architectures to distribute these reagents: broadcast sprinkler systems and precision drip irrigation networks. How a plant chooses to apply its fluids directly determines its total gold extraction yield, its daily operating costs, and its long-term environmental liability. The intuitive assumption is that laying down a heavy, widespread spray of reagent over the top of the heap will quickly and thoroughly saturate the rock underneath. The physics of porous materials dictates the exact opposite. Pumping chemical reagents at a high, continuous spray intensity physically limits how deep and how uniformly those fluids can permeate the pile. By blanketing the top layer with high-velocity water beads, sprinklers create structural barriers within the rock matrix. The ore looks completely soaked from above, but the chemical extraction process below is stalling out. Transitioning to a drip irrigation system solves this issue. This shift is a calculated re-engineering of the leaching environment's fluid dynamics and chemical thermodynamics. To understand why drip networks outperform sprinklers, we need to evaluate exactly what happens to the reagent by tracking its fluid dynamics, its chemical reactivity, and its overall mass balance. We can treat this as a physical modeling problem. We have to look past the wet surface of the rock pile and examine how liquids and gases actually move through the tiny empty spaces between the crushed mineral particles. This graph tracks spraying intensity against the rock's infiltration capacity. Initially, intensity is low. Liquid easily enters the interstitial spaces, mirroring natural rainfall, a state called free infiltration. But as intensity increases, liquid outpaces absorption. Water pools on the surface, hardening the top crust. At that exact threshold, the mechanics of the entire system shift. The heap transitions out of free infiltration and enters a state of pressure infiltration. Under pressure infiltration, the liquid no longer flows naturally through empty voids. Instead, it must exert mechanical force to push through that hardened, saturated upper boundary layer. Because the downward flow is choked, the chemical reagent cannot rapidly reach the dry mineral powder deep inside the pile. The washing effect is severely slowed down. By applying too much liquid too quickly, sprinkler systems engineer their own physical bottleneck, structurally preventing the chemical from contacting the gold efficiently. Now consider a precise industrial drip emitter. Instead of a broad spray, it applies single concentrated droplets of reagent directly to the crushed rock. This side-by-side comparison illustrates how drip systems resolve the infiltration paradox. Because the application rate is strictly controlled on the right side, the fluid volume never crosses the infiltration capacity threshold of the mineral powder. The pooling and hardening effects disappear, allowing the drip architecture to maintain a continuous state of free infiltration indefinitely. The leaching reagent flows downward without resistance, washing the surface of the gold mineral powder throughout the entire pile. This introduces a critical advantage: aeration. Because the voids aren't choked with excess water, oxygen can freely mix with the downward flowing liquid. In the thermodynamics of gold extraction, cyanidation and alternative chemical oxidation processes require abundant oxygen to drive the reaction forward. Without oxygen, the leaching stalls. By eliminating that suffocating top layer of water, the heap is able to breathe. It actively draws air into the interstitial spaces, increasing the oxygen concentration available for the chemical reactions. Modern drip networks can also easily integrate temperature control equipment, allowing engineers to precisely heat the solution and further optimize the reaction environment. A drip line provides a highly oxygenated, thermodynamically active environment, directly boosting the rate at which gold is extracted from the ore. We can also measure efficiency by looking outward, evaluating the mass balance of the reagent at the atmospheric interface above the heap. This chart compares the percentage of chemical reagent loss to the environment. Sprinklers inherently atomize the liquid into tiny beads. That creates a massive surface area exposed directly to the open air. The reagent rapidly volatiles into the atmosphere. Wind drift carries toxic chemicals completely off the leaching pad, and intense solar UV rays degrade the active chemical compounds before they even hit the rock. Every drop of lost reagent requires purchasing replacement chemicals to maintain the required concentration. And when that uncontrollable spray creates hazardous runoff around the pad, the plant faces exponentially higher sewage treatment costs. Modern drip systems bypass these atmospheric hazards through their internal hardware. The emitters are equipped with built-in pressure compensation devices and anti-blocking technology. This ensures that the outflow remains highly uniform across the entire surface of the heap, even when navigating steep elevation changes or irregular terracing. Because the delivery is completely insulated from wind and evaporation, engineers can perfectly calibrate the reagent concentration and dripping strength to match the exact composition, grade, and crushing degree of the ore. Moving from an atomized spray to a closed, precise drip line effectively eliminates atmospheric mass loss, heavily reducing both chemical waste costs and environmental liability. Upgrading a delivery pipeline is an exercise in applied physics. It is a direct method to optimize both the fluid dynamics and the chemical thermodynamics of a mining operation. By preventing the structural bottleneck of pressure infiltration, a drip network ensures that continuous, high-efficiency chemical reactions take place directly at the surface of the ore. It also unlocks severe operational advantages, completely eliminating the negative influence of wind and allowing the leaching pad to operate continuously, year-round, regardless of harsh atmospheric conditions. The final variable to this system is the chemical itself. Many modern operations are replacing traditional cyanidation with eco-friendly gold leaching reagents like Jinchan. Pairing a precise zero-drift delivery system with these non-toxic chemical reagents creates a compounding effect, drastically lowering safety risks and slashing environmental compliance costs. The result is an extraction architecture that features simple installation, a high degree of automation, rigorous environmental protection, and vastly superior production efficiency. To achieve maximum extraction yield with minimal operational friction, a modern gold mine must engineer its fluid dynamics from the top down. That physical requirement makes drip irrigation the definitive industry standard.